Hello, everyone. Today, we discuss magic squares. I'm going to explain the fundamentals of magic squares, which are related to integer congruence. I will also explain an easy algorithm to generate a magic square. I'm going to use 5 by 5 squares as examples. They can be generalized to other dimensions. First, what is a magic square? Let's look at this example. It is a 5 by 5 magic square. Integers from 1 to 25 are arranged to satisfy several properties. First, row property. The first row, 14, 10, 1, 22, and 18 sum up to 65. The second row also sum up to 65, so as the third, the fourth, and the last row. Secondly, we have a column property. All the columns also sum up to 65 as well. The third property is called diagonal property. The first diagonal, 14, 11, 13, 15, and 12, has sum 65. The other diagonal also sum up to 65. We have another property called symmetricity. So 13 is placed in the center of the square, and the largest number of 25 and the smallest number 1 are placed in a symmetric position to the center, 1 and 25. So as the second largest 24 to the second smallest 2, also symmetric to the center, 2 and 24, 3 and 23, 4 and 22, and so on. Let's have a quick summary regarding the key properties for magic squares. First, we have a row property, and we have also column properties. And the third one is the symmetric property. The symmetric property is stronger than diagonal property. In other words, it implies the diagonal property. Why? We can take a look this example. So 13 and 12 are symmetric. They sum up to 13 plus 13. So as 11 plus 15. So the diagonal sum up to 65 automatically if it is symmetric. In the literature, people define magic squares to be the one with row property, column property, and the diagonal property. In this video, I'm going to use a relatively stronger definition, replace the diagonal property with symmetricity. Before we study the property of magic square, we make a simple transform. Reduce each number by 1. This is the magic square. All numbers are subtracted by 1. So 13 minus 1, 14 minus 1 is 13, 10 to 9, 1 reduced to 0, and so on. So the new range of the numbers is from 0 to 24. Of course, the row column properties are also satisfied. In the new table, the sum of a row, a column, or a diagonal would be 65 minus 5, which is 60. They are symmetric as well. After the transform, we can rewrite these numbers in quinary expressions in five-based. 0 equals 0 times 5 plus 0. So I express it in 2 digits expression 0, 0, 5-based. 1 is 0, 1, 5-based. 2 is 0, 2, and so on. So 5 equals 1 times 5 plus 0. So 5 is 1, 0, 5-based. We go all the way to the end. 22 is 4 times 5 plus 2. So it can be expressed by 4, 2, 5-based. And 23 is 4, 3. 24 is 4, 4. So all these 25 numbers are expressed in quinary expressions, all 2 digits from 0, 0, 0, 1 all the way to 4, 4. I'm going to introduce another table. This is the starting point. I call it natural arrangement. This is just from the smallest to largest, 0, 1, 2, 3, 4, the first row, and then 5, 6, 7, 8, 9, the second row, all the way to 24. This is a natural arrangement. And we can express all these numbers in quinary expressions, 0, 0, 0, 1, all the way to 4, 4. So for each expression, they have 2 digits. I used them in different colors for first digits and for second digits. We separate the table into 2 tables, one for the first digit, the other for the second digit. We can see that if all the numbers are divided by 5, then the first digits are simply the quotient. The first row divided by 5, the quotient is 0. The second row, the quotient is 1, and so on. And the second digit is simply the remainder when the numbers divided by 5. Now we are ready to look at the example we have for the magic square. First, we express all the numbers in quinary expression. Not much things to see, but we can separate this table into 2 tables by first digits and by second digits. This is the table for the first digit and the table for the second digit. You can see they have some patterns around there. But before we investigate the pattern, let me explain a fundamental property of magic square. Let's look at the table for the first digit. You see the first row, 2, 1, 0, 4, 3. It is a permutation of 0, 1, 2, 3, 4. The second row is also a permutation of 0, 1, 2, 3, 4, 3, 2, 1, 0, 4, and so as the third, the fourth, and the last rows. If you look at the column 2, 3, 4, 0, 1 is also a permutation of the 5 digits, and so as the second column, the third, the fourth, and the last. If you look at the second digit table, they have the same property. For the first row, 3, 4, 0, 1, 2. The second row, 4, 0, 1, 2, 3, and so on. The rows, the columns also have the same property. Let's summarize. Each row or a column have 5 2-digit quinary numbers. The first digits in a row or a column form a permutation of 0, 1, 2, 3, and 4. The second digit of each row or column also form a permutation of 0, 1, 2, 3, 4. Why this is important? You see, if you want to calculate the sum of five numbers in a row or a column of a magic square, then you sum up all the first digits times 5 and plus the sum of all the second digit. This is something like 5 times 0 plus 1 plus 2 plus 3 plus 4 plus 0 plus 1 plus 2 plus 3 plus 4, exactly 60. So this is the fundamental property for generating magic squares. Let's look at another magic square. Quinary expressions separated into two tables. You see the first digit 1 3 0 2 4, the second row 2 4 1 3 0, and so on. You see they are all permutations of 0 1 2 3 and 4, so as the table of the second digit. We can look at this property in a different perspective. So, in other words, each row or column in the natural arrangement must be allocated in a different row and a different column in the magic square. The first row, 0, 1, 2, 3, 4. You see, in the magic square, they are all in different rows, different columns. But at this moment, let's take a look at the pattern. So I'm going to use the pattern to derive the algorithm of generating the magic square. So let's first, we put some 0 somewhere. From 0 to 1, you see the 0 in the second row, third column. 1 is the third row, second column. So the movement from 0 to 1 is down by 1 row, move left by 1 column. That's from 0 to 1. From 1 to 2, we follow the same pattern. Down by 1, left by 1. From 2 to 3, down by 1, left by 1. However, 2 is on the first column, so we move all the way to the end, to the fifth column, to form a cycle. So 3 is put in the corner. And then down by 1, go all the way up, and right by 1. That's where 4 is placed. And then down by 1, right, left by 1, we go to 0, form a cycle. The second row followed exactly the same movement or pattern, 5, 6, 7, 8, 9. And the third row, 10, 11, 12, 13, 14, perfect. And the fourth row, the fifth row. We can also look at the columns. You see the first column, 0, 5, 10, 15, 20. You see in the magic square, they are placed in a different rows and different columns. They also have some patterns. From 0 to 5, move down by 2 rows, move right by 1 column. And from 5 to 10, it's exactly the same thing, 10 to 15, 15 to 20, and from 20 to 0. The second row, the second column, the third, the fourth, and the last column. After that, we look at the pattern for diagonal. 0, 6, 12, 18, and 24. So in the natural arrangement, they are in different rows and different columns. So we don't need them to be in different row or column in the magic square. So this is no longer related. But we want to look at the pattern. 0, 6, 12, 18, 24. Let's see, from 0 to 6 in the magic square, down by 3 rows, or you can look at it in different way. You go up by 2 rows. Go up by 2 rows from 0 to 6, the second row to first row to the fifth row. And from 6 to 12, up by 2. From 12 to 18, up by 2. And 24, and back to 0. Let's look at another example. This is a magic square I introduced before. First row, second, third, fourth, fifth, and also column. So you can see the patterns. Now we are ready to discuss the algorithm. First, the number 0 can be anywhere except the center of the square. We know the center of the square is reserved for the number 12. So in this example, we put 0 in the position of the second row, first column. By symmetricity, we put 24 on the other side, the fourth row, fifth column. In the natural arrangement, 0, 12, 24 are all in the diagonal, 0, 6, 12, 18, 24. Then the question, where should we put 6 and 18 in the magic square? We know 0, 6, 12, 18, 24 form a pattern. So here is the pattern 0, 6, 12, 18, 24. But how do we get the pattern? There's many ways. Here's my suggestion. We already have the position for 0 and 24. We start with 24. From 24 to 0 to 6 to 12 to 18 also form a pattern. So from 24 to 0, you see in the magic square, we move up by 2 rows, move right by 1 column. Up to right 1. Up to right 1 to 6 and 12 in the center as expected, and then 18. That's how I get it. Now, let's see if we put the 0 in the corner, first row, first column. Then all the diagonal numbers, 6, 12, 18, 24, should be put exactly the same position in the natural as the natural arrangement. Another example, if we put 0 in the second row, second column, we have to put 24 in the fourth row, fourth column. Then from 24 to 0, move up by 2 rows, move left by 2 columns, 24 to 0, and then the next one is 6, 12, 18. This is the pattern, okay? And another possible solution for 0, 0, 6, 12, 18, 24. So this is the first step. We put 0 in anywhere except the center, and then find the positions for all numbers in the main diagonal of the natural arrangement. The next step would be the position for 1. 1 can be anywhere except the same row or same column for 0 and 6. Why? You see, in the natural arrangement, 1 and 0 is in the same row. 1 and 6 is in the 6th column. Then they shouldn't be in the same row or same column in the magic square. Let's look at this example. So I black out all the rows or columns determined by 0 and 6. And the other diagonal number 12, 18, and 24 I also labeled, except these positions, 1 can be anywhere else. For example, we place the number in the 3rd row, 5th column. Then we are ready to place all the numbers in the 1st row of the natural arrangement. We already have 0, 1, then 2, 3, 4, just follow the pattern. From 0 to 1 in the magic square, move down by 1 row, move left by 1 column. Then down 1, left by 1, we got 2, and 3, and 4. For the 2nd row, we don't know where to put 5. Fortunately, 6 already there. Then we start from 6, follow the exact same pattern to place 7, 8, 9, back to 5. For the 3rd row, we start with 12, and then 13, 14, back to 10, and 11. And then we do the similar trick for the 4th row and the 5th row, and the magic square is created. So in the algorithm, there's a 2 step. 1, to place 0. And from 0, we find all the positions for the main diagonal numbers 0, 6, 12, 18, and 24. And then we exclude all the rows or columns determined by 0 and 6, put 0 anywhere. And then in the 2nd step, we created all the rows according to the pattern from 0 to 1. Then we are done. Before I conclude the video, I'm introducing 2 interesting magic squares. The first one is called the even-odd separation. So this one we already seen it. So the even-odd separation means all the even numbers are placed in the 4 corners, all the green numbers, in the 4 corners of the squares. And the odd numbers are put in the center. So you can create even-odd separation magic square for all odd number dimensions, like 3 by 3, 5 by 5, 7 by 7, 9 by 9, and so on. So here is another example, 7 by 7. So you can pause the video to study the pattern. So you see for all the odd numbers start with 1. 1 is placed in the center of the 1st row. And then you see move all the way down by 1 and right by 1, 1, 3, 5, 7, and 9, 11, 13, 15, 17, and so on. The pattern is pretty obvious. Another type of interesting magic square is the embedded magic square. So this is an example of 9 by 9 magic square. So the number is from 1 to 81. The whole big table is a magic square. And it is also partitioned to 9 smaller squares, 3 by 3 cases. All these squares are magic squares. This is a very interesting one. Well, that's all I have today. Thank you for watching.